So in the previous video, we saw the derivation of the Kirchhoff's condition and in its application to the 4-bar chain. Now we will understand a very important concept in 4-bar chain or for mechanisms in general, that is called inversion. So if you recall our definition of the mechanism is obtained by fixing one link of a kinematic chain. So by fixing different link of kinetic chain, you can get different mechanisms. So inversions are nothing but different mechanisms obtained from same kinematic chain by fixing different links. So you may come across sometimes two mechanisms which look very different from each other, but if you go on at a basic level and simplify them, you will realize sometimes that they are derived essentially from the same kinematic chain. So the 4-bar chain is quite important kinematic chain. It's a basic building block of many other complex chains. So we will study here inversions, Grashoff's 4-bar chain. Similarly, we have inversions of the non-Grashoff 4-bar chain and the special Grashoff 4-bar chain. So in our previous video, we saw that the 4-bar chain mechanism can be classified into 3 categories: class 1, class 2 and class 3, that is Grashoff's, non-Grashoff's and special Grashoff's. So for Grashoff's 4-bar chain, that is the criteria is length of the longest plus the length of the shortest link must be lesser than the sum of length of other two links. The mechanisms obtained from such a chain which satisfies Grashoff's condition are dependent or based on the position of shortest link. So there are basically 3 categories of inversions of Grashoff's 4-bar chain that depends on the position of the shortest link. That we will classify here. For that, I'll just sketch a Grashoff mechanism here. So this is the shortest link, this is the longest, these are the other two links. So the first category is the one where link adjacent to the shortest link is fixed. So from this category we get a Crank-Rocker mechanism. I'll just sketch that for you. So if you are going to fix the link L, which is longest link, or P, which is an intermediate link, both of those are adjacent to the shortest link. If you fix any of these two, you will find that you have a mechanism where the shortest link is able to make a complete turn. So in such a mechanism, whether you fix this link or this link, in any case, the shortest link will be able to make a complete rotation, complete 360-degree rotation. So it will serve as a crank, as a crank. The shortest link will be as a crank, and the other link maybe it can have a continuous, and for the other links, that one of them is fixed, the other two links will have a rocking motion. So while this is rotating, the shortest link is rotating full 90 degree, the Q will have a rocking motion, and correspondingly P will also have some rocking motion. So that's why it is called a crank rocker mechanism. So this is a category with shortest link acting as a crank, and you have link adjacent to the shortest link fixed. The second category is the one where the shortest link is fixed. So the mechanisms under this category come under double crank mechanisms. So we have the shortest link here that is fixed to the ground, and we will draw the other links like this. So this is the shortest link which is fixed, and these are the other links, which means P, Q, L, longest link. So if you consider the geometrical motion of this mechanism, you will find that while P can do a complete rotation, likewise the link L can also do a complete 360-degree rotation. So you have complete rotation of link P and L if the shortest link is fixed. So that's why this is called double crank mechanism, because you have two cranks here. So any of the two links, it may not be necessary that the longest link should be adjacent to the shortest link. The longest link can be this one, it can be an intermediate link. But just by fixing to the shortest link, you will get a rotational motion of two links and completely rotate. And that's why it's called double crank mechanism. The third category is the one where the link opposite to the shortest link is fixed. This category results in a rocker mechanism. So I'll do a sketch for you. In this mechanism, you can see that the shortest link is this one and the longest link is this one. So here the link opposite to the shortest link is this, that we can join by a dotted line here. So the link opposite to the shortest link is fixed here, and we get a rocker motion of these two links. So the complete rotation is not possible of these two links adjacent to the shortest link, but we get a rocker arrangement motion of these two links P and Q. The interesting thing to note in this mechanism is that by the motion, the rocking motion of P and Q, you can get a complete rotation of smallest link. That is possible. So if you recall our definition of Grashoff's mechanism, it was stated that Grashoff's mechanism has at least one crank. So whatever the inversion of the mechanism is there, like inversion means you are having essentially the same kinematic chain, but you are fixing different links. So still, if it is a Grashof mechanism, it should satisfy the condition that at least there is one crank. So at least one motion is possible. So if you fix the link opposite to the shortest one, and you get a rocker mechanism, so only rocking motion of two links is possible. They are adjacent to the shortest link, and the link opposite to the shortest link is fixed. Still, complete rotation of the shortest link is possible, and the Grashof condition is satisfied. So these are the three inversions of the Grashof's chain. So first you saw the link adjacent to the shortest link is fixed. This is a crank rocker mechanism. One is crank, other one drop. The second one is the shortest link fixed. In this case, you get double crank mechanism. We have two cranks, both having complete 360-degree rotation. The third condition is a link opposite to the shortest crank is fixed. In this case, you get rocking motion of two links adjacent to the shortest link, and you can have complete rotation of the smallest link. So now we will come to the inversion of the non-Grashof chain. Inversions of non-Grashof 4-bar chain. So if you recall the non-Grashof chain, that is a class 2 chain, it is satisfying the criteria that length of the longest link plus length of the shortest link is greater than the sum of the length of the other two links. While in Grashof's condition, it was otherwise. Like the sum of these two was less than the sum of the other two. So what we studied there is that in a non-Grashof mechanism, you can have only rocker motion arrangement possible. You cannot have any crank if this condition is if the Grashof's condition is not satisfied. The Grashov condition is necessary for complete rotation of one of the links. So you can have only rocker mechanism. So if you fix any of the links in a non-Grashof chain, so I'll draw it here for you. So in this case, as you can see, the longest link is very long, and this is the shortest link. The sum of these two is greater than the sum of the other two intermediate links. So if you fix any of the links in this kinematic chain, whether you fix P, Q, L or S, you can only get a rocker motion. Also, because complete rotation of any link is not possible, will result in a rocker arrangement only. Now we will come to another topic, that is inversion of special Grashof chain. So if you recall the condition for special Grashof chain, it was that the length of the longest link plus the length of the shortest link is equal to the sum of the length of the other two links. In the case of special Grashof chain, we again have two subcategories. One is called parallelogram chain. In this case, the link of the opposite link, like if you see this diagram, the link Q is opposite to link S and L is opposite to P. So the opposite links are of equal length. So S will be equal to Q in this diagram and L will be equal to P. So this is called a parallelogram chain. In such a mechanism, you will see that a parallelogram is constructed. So S, L, L. Opposite links are equal. The other category is anti-parallelogram chain. In this case, the above condition is not satisfied. So any of the above mentioned condition, either S will not be equal to the opposite link or this link will not be equal to the opposite link. Any of the above condition is not satisfied, then it will be an anti-parallelogram. That means a parallelogram will not be formed. So we will consider both of these cases. So in the case of the parallelogram chain, we have the diagram like this. So if you talk about inversions, like we discussed earlier, inversion are the different mechanisms obtained by fixing different links in a kinematic chain. So in this case, even if you fix any of the link, if you fix this link, you will get a complete rotation of this link, the shortest link, and the complete rotation of the opposite link, opposite shortest link. Likewise, if you fix the shortest link, you will get complete rotation of the longest link and same complete rotation of the opposite link to the longest link. So complete rotation. So this is the crank mechanism. This is the property of the parallelogram chain. Another interesting property to note here is that the crank circles, the circles traversed by the crank are identical. So this is a very useful property, and it is employed at many places, such as you may be aware of your engineering drafter. So you have a drafter linked to the frame, then in the frame you have an element like this. So it's having links connecting to the another element, similar element. So if you consider this kinematic chain, so there is one link, there is parallel link, in the parallel link. So you will get a parallelogram linkage here. So a parallelogram chain is formed here. This is the shortest link, this is the longest link, L, L, S and S. Likewise, in the drafter, you see that one more element is there, similar element, and it is also again joined by parallelogram connections. So in this case, there is a limited mobility due to the links overlapping each other, and in the end, you have the drafter scale. So here, the motion of the drafter scale will be parallel to parallel at any angular position, and this is maintained by the parallelogram chains property that the crank circles are identical. Another application of this mechanism you can see in train and locomotives wagon wheels. So this is the center of the wheel. So there you see some off-center crank. So these two cranks are joined together. So by this means the force or torque from one wheel is transferred to other, and the load is evenly distributed. So here also you can see that this is a parallelogram mechanism with the longest link fixed, and these two cranks do a complete 360-degree rotation. So this is our application drafter and locomotive. Now, in the parallelogram chain, we stated that it is formed when the opposite links are of equal length. We may also have one variation of the special Grashof chain, that means L plus S is equal to P plus Q. This condition is satisfied, but it is not a parallelogram. So that special case is called a deltoid chain. Deltoid connection, in deltoid connection, the criteria that L plus S is equal to P plus Q is satisfied, and also S is equal to P and L is equal to Q. However, the difference is that the shortest links are adjacent to each other and the longest links are adjacent to each other. So L is adjacent to L, S is adjacent to L. This is also condition wise satisfying the criteria of parallelogram chain, but the condition that the opposite link should be of equal length is not satisfied here. This is called a deltoid chain. What about the inversions of a deltoid chain? In deltoid chain, fixing any link in the mechanism basically is a symmetrical mechanism. The S and S, L and L symmetrical mechanism. So you have two possibilities of fixing. You can fix the longer link. Then you can have complete rotation, 360-degree rotation of the shorter link and rocking motion of the longer link. If you fix the shorter link, then the other shorter link can have a complete 360-degree rotation, and this one can have rocking motion. So in both cases, you get a crank rocker mechanism. So in deltoid chain, if you fix any of the links, this condition is satisfied. There are two short links of equal length, two long links of equal length, and fixing any of the links in the chain, a crank rocker mechanism is obtained. Understanding these concepts is important because in GATE examination, you will find questions like there will be a problem given, like a name will be given, deltoid chain, parallelogram chain, and the corresponding conditions will be asked. What is the Grashoff's condition for that? What is the special property of this mechanism? By fixing some link in the chain, what kind of mechanism can be obtained? What are the inversions of the mechanism? These kind of questions will be asked. That will be illustrated shortly. Now, the other category in the special Grashoff chain was the anti-parallelogram chain. In this case, the opposite links are not equal, or even the adjacent links are not equal. So it is not parallelogram. It is not deltoid, but it satisfies L plus S is equal to P plus Q. So I can sketch a representative mechanism here, not to the scale. So here the condition satisfied is that S plus L is equal to P plus Q. This is a special Grashoff chain, anti-parallelogram chain, which is not common in parallelogram, and it is also not a deltoid. That means the adjacent links are not of equal length. So the property, what are the various mechanisms obtained by inversion of this chain? By fixing any link, we get a double crank mechanism. So in a double crank mechanism, if you fix the link, there are two cranks. So complete 360-degree rotation is possible for two links. So this is the double crank mechanism. There are two cranks in the system, CC crank. So if you recall our earlier discussion on the Grashoff's class 1 kinetic chain, if you fix the shortest link, that also gives a double crank mechanism. So what is special about this case? In this present case, it is satisfying the special Grashoff condition L plus S equal to P plus Q. So the condition here is that any link can be fixed to obtain the double crank mechanism. While in Grashoff class 1, only the shortest link has to be fixed to get the double crank. In this case, any link is fixed. This link also will get a double crank motion of the adjacent links. Typical application of the double crank mechanism is observed in the steering gear where rotary motion from the steering wheel is transferred to the transmission wheels, that is the driving wheels. So you have a steering wheel, there is a rotary motion, it is connected by chain, and in the steering gear chain you get the rotary motion of the frame. So actual mechanism is quite complicated, it is not drawn here. So this is the application of the double crank mechanism. Other application of double cranks we saw earlier was in a drafter or locomotive transmission, but there the special condition was that the links were parallel to each other. In the drafter and a locomotive, these are also double crank. But here, since the links are parallel, the circles that are formed by rotation of these links are identical. In double crank, which doesn't satisfy the parallelogram condition, not satisfying parallelogram condition, you can get an amplification of the rotary motion. So the two circles which are circumscribed by double crank mechanism may be of different size and different angular position, different start and end position. In the steering wheel mechanism, we want that a large motion of steering wheel results in small motion of the locomotive wheels to maintain the accuracy. So to get different kind of motion, the double crank mechanism may be used. So now we will just quickly revise what we have learned till now in the category of 4-bar chain. So in GATE examination, typically the questions asked are about the category of the 4-bar chains, how they are classified in different categories, and what kind of mechanisms or formations are possible, like crank rocker. So these kind of things you need to keep in mind. The 4-bar chain, the basic condition for its formation is that length of the longest link should be less than the sum of the other 3 links. So that's how a triangle formation is possible. So that's how the link formation is possible. After that, further categorization takes place according to Grasshopp's condition. So Grasshopp's condition is applied that whether L plus S is greater than, equal to, or less than P plus Q. So according to that Grasshopp's condition, we will classify the mechanisms as Grasshopp's mechanism, where L plus S is less than P plus Q. This is called Grasshopp's. If the class 1 condition is satisfied, that is Grasshopp's condition, then we have various inversions of the Grashopp chain possible. So these inversions are: if shortest link fixed, then it results in a double crank or a TC mechanism. If link adjacent to shortest link is fixed, we get a crank rocker mechanism. And if the link opposite to shortest link is fixed, we get a rocker mechanism. The other class is non-Grashopp or class 2. Here the condition is L plus S is greater than P plus Q. So L is the length of the longest link, S is shortest link, P is the length of the intermediate link. In this case, fixing any link results in rocker-rocker. So only one category is possible. The other category is spatial Grashof. Spatial Grashof, the condition satisfied is L plus S is equal to P plus Q. This is called class 3 Grashof mechanisms. Here you can have parallelogram, anti-parallelogram and deltoid. So the parallelogram is a symmetrical mechanism. It results in a crank-crank mechanism where the circles formed are equal. So same rotary motion transmission, same kind of motion is replicated at some other location. This is a special property of the parallelogram mechanism. It is forming crank-crank. And so in an anti-parallelogram configuration, the special property is that fixing any link results in a crank-crank or double crank mechanism. So earlier we saw that for the Grashof class 1 mechanism, fixing the shortest link results in a crank-crank. But here, in the anti-parallelogram case, fixing any link will give you a crank-crank. The last category is the deltoid mechanism, where the L plus S is equal to P plus Q is conditionally satisfied, but the shortest links are adjacent to each other, and the longest link are adjacent to each other. So it is drawn like this, SS, if you recall. You can visit the earlier portion in the video. And in the grand deltoid connection, fixing any link will result in a crank-rocker arrangement. Crank-rocker, crank-crank, crank-crank. These are three categories in the spatial Grashof. And in non-Grashof, fixing any link will result in rocker-rocker. Rocker-rocker. So for the GATE examination, this flowchart is all that you need to remember. That what is the Grashof condition, what are the different kind of combinations possible according to the length of the links, how can you classify, and there will be a simple objective question where you have to choose the correct answer. Like what is the Grashof condition, and by fixing the shortest link in a Grashof condition, what kind of mechanism is obtained. This kind of questions will come.